Now we're going to look at identifying local behavior of polynomial functions. So we talked about the end behavior. So as x gets really big or really small, what happens? Like it's going to go way up, go way down. The local behavior is more talking about where it's going to cross the x-axis, the x-intercepts, and turning points, where it's going to go from going increasing to decreasing or decreasing to increasing. So those are these concepts known as local behavior. Local meaning is going to be more in the middle stuff instead of the more extreme values. So intercepts and turning points of polynomial functions. A turning point of a graph is a point at which the graph changes direction from increasing to decreasing or decreasing to increasing. The y-intercept, let's make that bold, by the way. The y-intercept is the point at which the function has an input value of 0. So x is 0, and it produces the value y where it hits the y-axis. The x-intercepts are points at which the output value is 0, because y is 0 on the x-axis. So how to determine the intercepts of a polynomial function? Determine the y-intercept by setting x equal to 0 and finding the corresponding output value. Determine the x-intercepts by solving for the input values that yield an output value of 0. So you take the function and set it equal to 0. So for example 8, it says given the polynomial function, written in factored form, determine the x and y intercepts. So for our y-intercept, we say x equals 0. And remember, this is going to be at most one y-intercept. So we're going to have f of 0 is 0 minus 2 times 0 plus 1 times 0 minus 4. That's going to be negative 2 times 1 times negative 4, or 8. So 0 for x is 8 for y. The x-intercepts, and there could be more than one. There could be 0, by the way. The x-intercepts, we're going to take x minus 2 times x plus 1 times x minus 4 and set that equal to 0. And fortunately, they already factored this for us. Obviously, the next problem they didn't factor for us, but we'll manage. So x minus 2 is set that equal to 0, so x equals 2. X plus 1 would set that equal to 0, so x equals negative 1. And x minus 4, we set that equal to 0, so x equals 4. So our intercepts are going to be at, make sure I stay within my window, 2, 0, negative 1, 0, and 4, 0. For example 9, it says given the polynomial, f of x equals x to the fourth minus 4x squared minus 45, determine the y and x intercepts. So again, our y-intercept is going to be f of 0. So 0 to the fourth minus 4 times 0 squared minus 45 is negative 45. So that's going to be at 0 for x, negative 45 for y. But our x-intercept, that's going to be where x to the fourth minus 4x squared minus 45 equals 0. So we're going to have to factor and solve this. So I don't know if this helps. I'm going to do u substitution. U equals x squared. This is u squared minus 4u minus 45 equals 0. So this would factor to be u minus 9 times u minus 5, or plus 5, excuse me. So u minus 9 equals 0 means u equals 9. U plus 5 equals 0 means u equals negative 5. But we're not finished because we have to go back and say what was u. U is x squared. So x squared equals 9 means x is plus or minus 3. So we have 3, 0, and negative 3, 0. X squared equals negative 5 means x equals plus or minus the square root of negative 5, which would be plus or minus I root 5. So we have I root 5, comma 0, negative I root 5, comma 0. Now, I want to point out the last two that with i's, those are imaginary. They're not crossing the x-axis. And what we'd see is if we had a graph that, and I'm just making this one up, so it'd come down, cross at 3, may do something like that. I don't know, something like this. Maybe come up and go down, come up, come down. If I do this, it might erase the whole, yeah, it does. Okay. So meaning that that and that would be the imaginary roots. So, okay, and that's it for talking about local behavior of polynomial functions.